Hi guys, my name is IBM and today I decided to solve past papers, especially in paper 5, that is planning, analysis and evaluation. My friends and my students asked me to record at least some paper 5s, and today I decided to create a few videos for paper 5. And without wasting time, I would like to show you which paper I'm trying to solve. So today I'm trying to solve Paper 5, Planning, Analysis and Evaluation. This is going to be October, November 2019. The paper is 1 hour and 15 minutes. This is 970253. So without wasting time, I would like to take you to this paper. This paper is normally 30 marks. Each question is 15 marks. There are always two questions. The first question is for planning. The second question is analysis and evaluation. So let's start with the first question. So when a light plastic ball is placed in a vertical column of air, the ball becomes stationary at a height h as shown in the figure. A student is using an air blower to create the vertical column. So the student must create a vertical column of air. So what normally would create a vertical column of air? Maybe you may need a fan. You may need a fan to create a vertical column of air. The student connects the motor to the air blower, so we need a power supply to run the motor. We need a DC power supply to run the motor. Of course, you should be knowing the symbol for a DC supply. It is suggested that the relationship between the radius r of the ball and h is given by this expression here. So the radius and h, that is their relationship. G is the acceleration of free fall, P is the power of the motor, so we shall know that power is going to be I times V, so we need an ammeter and a voltmeter in order to be able to determine power. And K is a constant. Design a laboratory experiment to test the relationship between R and H. Because I'm going to test the relationship between R and H, I have to choose which one is in my reach to change, that will be the independent variable, and which one changes when I change the independent variable, that will be the dependent variable. So in my reach, or on my side as the experiment, it is easier for me to change the radius of the ball by choosing another ball of a higher radius or a smaller radius. So the radius will be the independent variable. And when I change the radius, I expect it for the same air column, I expect it to go to a different value of h. So h is going to be the dependent variable. So of course, I'm going to design an experiment to test the relationship between r and h. And I'll use the experiment to determine the value of k. So before I go any further, I've already identified the independent variable and the dependent variable, and I'm going to keep the power constant. So the power is going to be the control variable. Power is going to be the control variable. So the best way to carry out to plan an experiment is to look at the independent variable, the dependent variable, and the constants. The simple formula I always give my students is that measure, vary, and improve. In other words, for every quantity, talk about how it will be measured, how it varies or how it will be varied, and if possible, how it will be improved. These three letters are very important: measure, vary, improve. How will it be measured? How will it be varied? And how will it be improved? So, for instance, the radius, talk about the radius. How will it be measured? Of course, it is not easy to measure the radius directly. You'll measure the diameter. And how will you measure the diameter of a plastic ball? So here you may use a micrometer screw gauge, or you may use a digital vernier caliper to measure the diameter. Then how will you improve? You'll measure around the ball and then obtain the average. And how will you vary? How will you vary the diameter? You'll pick another ball of a different diameter. So you are varying the diameter. Then of course, when the diameter varies, we expect that the dependent variable also changes. So how will you measure the dependent variable, which is h? I will use a ruler to measure h. Of course, I will not vary h because it will change on its own. So I'll use a ruler to measure h. And how will you make it? How will you improve the value of h? For this ball which is moving upwards, it is hard for me to measure up to the center. So I think for this particular experiment, it is easier to measure h from the bottom to the air blower, and I measure h to the top up the air blower. So if this is h1 and this is h2, it is easier for me to see that h1 plus h2 divided by 2 will give me the best value of h. So here I have improved h. That means I'll measure h to get a better value for h. I'll measure to the bottom of the ball and to the top of the ball and divide by 2 to be able, because it's hard for me to measure up to the center of the ball when it is in space or it is in air. Okay. Then next, you think about power. How do you measure? How do you make power constant? Of course, it means you're going to use a variable power supply, so that every time the power changes, you add just to take it back to its original value. Then which graph would you plot? That is now for analysis of results. So from the expression, I will make the dependent variable the subject. So making the dependent variable the subject, or something related to the dependent variable the subject. From the equation given, I notice that h is going to be 3pk divided by 4 pi g times r cubed. Remember, r was the independent variable. So any student who is very intelligent or who is very smart will easily choose which graph to plot. If I have h is equal to 3p over 4 pi g times r cubed, a student who is smart will notice that it is easier for me to plot a graph of h. I'll plot h versus 1 over r cubed. And you notice that there is no y-intercept. There is nothing here. If I compare with y is equal to mx plus c, there is no y-intercept, so this graph will go through the origin. So the student knows that this line goes through the origin, it goes through 0, 0. Since it goes through the origin, you also compare m with this quantity here, as this student will also see that the gradient is going to be 3pk divided by 4 pi times g. That will be the gradient. So the student will be able to see that that will be the gradient. So this student is now ready to plan this experiment, having drawn a skeleton of what they need to think about. Maybe for safety precautions, um, first of all, because we need to raise the ball to a measurable value of h, then we may need a large stream of air, and that large stream of air may be dangerous to our eyes, so you may need to protect your eyes with goggles, eye protection, or you could use a wind screen. You could screen anyway, eye protection goggles could be necessary. Maybe you could also withdraw the ball with a tray. Instead of grabbing it with your hands, you may withdraw the ball with a tray, large tray, to withdraw the ball from the stream of air. So let's start. I'll begin with a simple diagram because I have to assemble this into a diagram. The diagram is very important. But before I do that, I've already said I've already chosen which one is independent and which one is dependent. So I'll come here and say in this experiment, R is the independent variable and H is the dependent variable. So what will I keep constant? I'll keep P, the power constant. So I'll say P will be kept constant. So how will I always restore P to the original value? P will be kept constant. I will use a variable DC supply. So by using a variable DC supply, which can be adjusted so that the same power is always supplied to the motor. So I want the same power to always be supplied to the motor. Then how will I collect and analyze data? So to collect and analyze data, I will take the following steps. Okay, so the first step, I have to build the experimental setup. So let me first draw the diagram that I think is most appropriate for this experiment. Remember, the diagram is going to be compulsory here. First of all, my setup will be on a bench. So I'll draw a bench, a horizontal surface. So I'm drawing a horizontal surface here. It's not easy to draw this, but I'm going to try. So I'll draw a horizontal surface because I don't have enough tools to use on my computer, so I'll just draw this manually. So I'll draw a horizontal surface. Of course, you can draw a better surface than mine. So this is going to be the bench. Or the table. So one, I need an air blower. So I'll simply use a motor for the air blower. If you don't want to use that, you can just draw almost the same diagram which was given in the question. The same thing to represent an air blower, but it should be, of course, connected to the motor. If you want, you can put there a fan. So I'll use an air blower, but I may want to direct the stream of air to in one direction or above. So I'll put an air blower somewhere. Let me first draw a motor here. So I have a motor. I'm going to fix this motor. The motor is I must fix it on the table. So I'll use a G clamp. So the motor must be connected to a power supply. So I'll connect this motor to a power supply because it must have power. So I'll draw a simple circuit which has an ammeter. Of course, it must have a voltmeter which is connected in parallel. Maybe I may need a switch, and so this will be the ammeter. So because I want to always adjust the power to go back to its original value, then I'll use a variable DC supply. So I'll use a variable DC supply. So to make it variable, I'll put an arrow in the supply to show that it's a variable DC supply. So this is the power supply to the motor. Now this motor must be fixed on the table because as it rotates the blower, it should not be moving so that our device is stable. So I must fix this. I'll fix it on the table using a G clamp. So this is going to be a G clamp. Okay, so for the symbols which are known, I don't need to label them because this is a voltmeter, I don't need to label it. This is an ammeter, I don't need to label it. But for the motor, I'm not using its correct symbol. So I'll have to tell the examiner that this is the motor. And for the blower, there is no specific symbol, so I just need to call this one. Here they called it the air blower, so I'll just call it air blower because there is no such a specific symbol for the air blower. So I'll just call this one air blower. Okay, so the air blower must blow the ball vertically upwards. So I must draw a representation of the ball just above in almost the same line as the air blower. So the ball should be somewhere here. So the ball should be circular. So that is going to be the ball. I'll draw just an arrow to show the direction of moving air as it has been done in the diagram. Okay, so this is going to be moving air. Okay, so remember I must measure the height h from the top of the air blower to the bottom of the ball, and the height h from the top of the air blower to the top of the ball. Then I divide by 2. So I need a ruler which must be vertical, and the only way I can ensure that the ruler is vertical is by putting a set square beside it. So I'll draw a ruler which must be clamped. So I'm drawing my ruler here. Because there is no specific symbol for the ruler, I have to label that this is a ruler, but then at least there is something which I can put to show that this is my ruler. You don't need to be waste a lot of time designing this ruler, but there should be something to show that this is a ruler. This ruler must be, you want to ensure that it's vertical. So because I may have several tools, I may use a different color for the set square, because I want people to see why I need a set square. The purpose of the set square is to ensure that the ruler is vertical. So I'm putting a set square besides the ruler with the table so that the ruler is vertical. Okay, so there is a set square there. And I have to ensure, of course, I must clamp the ruler, so I must draw a clamp besides here. I'll put a clamp, I mean a stand. So So this is the stand which is going to hold the ruler. So I need a clamp. This is not easy, but it's worth it. It's worth it a try. So for you can use a ruler to make the diagram look so nice. But me, because I'm drawing on a computer, so this is the boss holding the ruler. So I need okay. So now my this is going to be my clamp. This is going to be the ruler or the meter ruler. So this is a set square. So all these additional details I've given you marks. I've clamped the ruler, that is one mark. I've used a set square to show that the ruler is vertical, that is the second mark. I've put a power supply, that is the third mark. I have fixed the motor onto the table so that in case it is working and shaking, the apparatus does not move, that is another mark. Those marks are given additional details. Okay, so I have to show, I may show that I'm measuring from the bottom, which is of course not really very easy, but I'll be measuring from the bottom and even to the top, then to the top of the air blower, which is also not very direct because I've left a space between um, the air blower and the ruler, which introduces parallax error, but that is fine. So this, you can call this height, you can call this one H1, and you can call this one H2. Because we want H, you will say H is equal to H1 plus H2 divided by 2. So that's how you, I think the diagram is now complete. I can now continue with my essay. So to collect and analyze data, I'll take the following steps. Step number 1, I will build the experimental setup as shown in the figure above. Step number 2, because it is involving blowing the ball vertically upwards. So by the way, this is the plastic ball. I must cut off wind which comes from different directions. So I may need to close the windows and switch off the air conditioning. So number 2, if I start the experiment, I will close the windows and switch off air conditioning. Or I would use a windscreen to avoid drought. In other words, you put a windscreen around your apparatus so that you avoid wind blowing to, which would blow the ball away. So, or use a windscreen to avoid droughts. Okay, so I think I'm now ready for the apparatus for the real experiment. So now I'm going to switch on the motor. So step number 3, I will switch on the motor and obtain readings of the voltmeter and the ammeter. Why do I need these readings? It's because I want to determine the power. So I will say then I will determine the power. Then I will determine P from P equals to I times V. So I'll determine the power from P equals to I times V. Okay, then step number 4. Of course, I have not yet measured the radius of the ball. So I think 4 would come even earlier, but the order doesn't matter. Then to determine the radius of the ball, of a ball, I will measure the diameter. Of course, I can't determine the radius directly, so I will measure the diameter. I will measure the diameter, of course, of the ball. I will measure the diameter. I will call it. Let me call the diameter D. I will measure the diameter D of the plastic ball using a micrometer screw gauge. Of course, you would also use a digital vernier caliper, but I will use a micrometer screw gauge, but you could use a digital vernier caliper. It should be digital because it will have a better precision than a normal vernier caliper. So I'll measure the diameter D of the plastic ball using a micrometer screw gauge or a digital vernier caliper. So here I'm giving you several options because I'm not doing an exam, but in an exam you may not have that time to write alternatives. Okay, so I'm still on the same point of diameter. So how will I find the radius? Then this is a continuation of 4. I will take multiple readings of the diameter in different directions because I want to obtain an average in different directions and obtain the average diameter. But this is not enough to tell me the radius. So what is the radius? The radius of the ball is just diameter divided by 2. So you tell the examiner that the radius of the ball R is going to be the diameter, which I called D divided by 2. So that is, this point gives you almost 2 to 3 marks, or 2 marks actually, or 3 marks. You're measuring the diameter using a micrometer screw gauge. You are actually telling the examiner how you repeated the measurements to obtain the average, and you are talking about how to deduce the radius from the diameter. Then step number 5, I will now place the plastic ball on top of the air blower or above the air blower. I will now place the plastic ball above the air blower. Above the air blower and wait. Of course, I have to wait until it raises until it becomes vertical. So you have to wait for it to raise vertically until it becomes stationary. So and wait for it to raise vertically until it becomes stationary. So you have to wait for the ball to raise until it becomes stationary before you measure h. Then number 6, now you're going to determine h. I will determine h I will determine h, but how will you determine h? Here I showed you that the best way to determine h is you measure h from the bottom of the ball to the top of the air blower, and from the top of the ball to the bottom to the top of the air blower, then obtain the average. That would be the best value for h. That method would give you an additional mark for that explanation. So I will determine h from the meter ruler by taking the distance from the top of the ball to the top of the air blower I call this one top. I think I call that one h2. The top of the ball to the top of the air blower, I called it h2, plus the distance from the bottom of the ball to the top of the air blower. And I've called this one h1. So then divide the sum by 2. Then divide the sum by 2. In other words, I'm saying h is equal to h1 plus h2 divided by 2. That is a very important mark. In step number 7, of course, I will now remove the ball. You will not just grab it with your hands, because you want to replace the ball with another ball of a different diameter, because you have to change the radius, remember. So you have to choose a ball of a different diameter. You repeat the steps to measure its radius, and then place it on top of the air blower. So I will remove the ball and take another ball. Another ball of a different diameter. And which will proceed. I'm going therefore to repeat step 4, where I have to find the radius of the ball. Then step 5, where I place the ball above the air blower. and step 6. So I will remove the ball and take another ball of different diameter and repeat procedures 4 to 6 until I have 6 sets of results, until I obtain 6 sets of results. Of course, when I have 6 sets of results, the next thing is to plot a graph. Remember, in the preparation, we decided to we came to an agreement on which graph is most likely going to be plotted. I mentioned that you make sure that what is related to the independent variable is on the x-axis, and what is related to the dependent variable is on the y-axis. So on the x-axis we have 1 over r cubed, and on the y-axis we have h. Remember, the radius was the independent variable, so if I say 1 over r cubed, that makes sense. H was the dependent variable, and when I say plot h on the y-axis, it also makes sense. So I'm plotting h against 1 over r cubed. You could have plotted another graph. Maybe you would have plotted a logarithm. For instance, you would have plotted log h against log r, but I prefer to plot the simplest graph for this matter. So I'll plot a graph. So step number 8, I will then plot a graph. Plot a graph of h against 1 over r cubed. Of course, from the previous analogy on the first page, we saw that this graph is a straight line and it had no y-intercept. So in step 9, I will say if the graph is a straight line, if the graph is a straight line which goes through the origin, through the origin, if the graph is a straight line through the origin, then the relationship is valid. Then the relationship is valid. So if the graph is a straight line, then the relationship is valid. But then they wanted us to find k. So I have to state what k was. I think we had already done that analysis. From here, from that expression, you notice that the gradient is equal to 3pk over 4 pi g. So you just tell the examiner that k equals to, if I make k the subject there, k is going to be equal to 4 pi g times the gradient divided by 3p. So I'll just simply say k is equal to 4 pi g times gradient over 3p. That is another 1 mark. So number 10, I'll simply call said question number 10, k is going to be equal to 4 pi g times the gradient divided by 3p. In fact, here a straight line to the origin, then the relationship is valid. You would even mention that the gradient here, the gradient of that line was 3pk divided by 4 pi g, where k is going to be equal to 4 pi g. What am I writing? So k is equal to 4 pi g times the gradient divided by 3p. That is k. Then what is remaining is safety precaution. For safety, so I'll say for safety, I will use a tray to collect the ball and to prevent it from rolling on the floor or bouncing. Okay, so this will be now the end of my planning. Of course, it is not conclusive. You could have a better way of doing this. Let me just take you through what I have just written once more. In this experiment, R is the independent variable and H is, I'll just go through as I put a tick. And H is the dependent variable, that's one mark. P will be kept constant by using a variable DC supply, which can be adjusted so that the same power is always supplied, that is one mark. To collect and analyze data, I'll take the following steps. I'll build the experimental setup as shown in the figure. I will close the windows and switch off air conditioning or use a windscreen to avoid drought, that is a mark. I will switch on the motor and obtain readings of the voltmeter and the ammeter, and then I will determine P from P is equal to I times V. So you have told us how to determine P. To determine the radius of the ball, I will measure the diameter D of the plastic ball using a micrometer screw gauge or a vernier caliper, but should be digital. If you choose a vernier caliper, it should be digital because the manual vernier caliper is less precise. I will take multiple readings of the diameter in different directions and obtain the average diameter. So you told us how to find the average diameter and then give a conclusion for the radius. I will now place the plastic ball above the air blower and wait for it to raise vertically until it becomes stationary. That is another mark. You must wait for it to become stationary before you measure H. I will determine H from the meter rule by taking the distance from the top of the ball to the top of the air blower plus the distance from the bottom of the ball to the top of the air blower, then divide the sum by 2. So I have showed you how best to measure H. I will remove the ball and take another ball of different diameter. So this one I'm showing you how to change radius. I'm picking a ball of a different diameter and I'm repeating the procedures procedure 4 to 6 until I have 6 sets of results. I'll then plot a graph of H against one of R cubed. So I've suggested which graph to plot. If the graph is a straight line through the origin, then the relationship is valid. So I've suggested what to expect from the graph. Then they asked us to show how we can find K, and I've showed you that K will be 4 pi g times the gradient. And then I've given a safety precaution. For safety, I would rather collect the ball using a tray rather than leaving it to fall on the ground or switching off the motor and leaving it to fall. So this is for safety. So this is one way you would write that plan. Of course, here I've put only 1, 2, 3, 4, 5, 6, 7, 8. I've put here 8 ticks. 1, 2, 3, 4, 5, 6, 7, 8. 8 ticks. But then there are more, okay, 9 ticks, 10, 11, 12, 13. I've put 13 ticks here. There are more. It's because I've written more points. You can write as much as you want because you are aiming at maximizing 15 points. But more points are on the graph, putting a set square to ensure that the ruler is vertical, clamping the ruler, putting the power supply. This will give me at least, no, at most, it will give me all the 15 marks because I've written all the points necessary. Okay, so that is for question number 1. Without wasting time, I want to go to question number 2. A student is investigating the oscillations of a mass attached to 2 springs connected in series as shown. So we can see 2 springs connected in series as shown. The stopwatch is used to measure the time t. So small t is time for 10 oscillations. The measurement of t is repeated and the average period t is taken. So if the measurement of t is repeated, it means the period is equal to t1 plus t2 divided by 2 for 10 oscillations. Again, divide by 10 to find one oscillation because this is the average of the 2 measurements. Divide by 10 to get the period. So in other words, the period capital T is equal to T1 plus T2 divided by 20. that is capital T, the period time for one oscillation. The experiment is repeated for different masses. It is suggested that T and M are related by that equation, where K is the spring constant of the two springs in series and Q is a constant. A graph is plotted of log T against log M. So I must make log T the subject. So introducing log, this will be log of T equals to log of, remember I need log M also, so I'll say log of 2 pi divided by root of K plus the log of capital M power Q. I just split this into two parts. So since I need log T over log M, I can still go take this further. So this will be log of T equaling to Q log of M, then plus a log of 2 pi divided by the root of K. So if I compare this equation with the y equals to m small mx plus c, it means on the y-axis I have log. On the y-axis I have log of t. On the x-axis I have log of m. So it means the gradient is q. So the gradient is going to be q. Automatically the y-intercept is going to be this. So the y-intercept is going to be log of 2 pi divided by root of k. So that is the y-intercept. Okay. Then values of m, log m, and measurements of t are given in the table. Okay. So calculate and record the values of t in seconds, log t in seconds in the figure. So let's remember I said the capital T, which was the time for one oscillation, was T1 plus T2 divided by 20. Okay, so let's first find T. Change the color to blue. So we are finding T. I'll just check with my calculator. For the first one, 15.2 plus 16.0 divided by 20. So that is 1.56. So you must maintain the same number of significant figures here. So this will be 1.56. Then 18.3 plus 17.5. This is divided by 20. So that is 1.79. 1.79. 19.3 plus 20.1 divided by 20. So this is giving me 1.97. Then we have 21.0 plus 21.8 divided by 20. So this is 2.14. Then we have 23.5 plus 22.7 divided by 20. So this is 2.31. And we have 24.1 plus 24.9 divided by 20. And this is 2.45. 2.45. Remember, we have to include the error, we have to include the absolute uncertainty in t in seconds and also absolute uncertainty in log of t. So what will be the absolute uncertainty in t here? Remember, for repeated measurements, absolute uncertainty is half of the range. So the absolute uncertainty in t, small t alone will be half of the range. Then it means the absolute uncertainty in capital T will therefore, because we first divided, of course, half of the range means T1 plus T2 divided by 2. Then for T, it will be equal to, of course, I'll just say the range divided by 20. Range divided by 20, because half of the range again divided by 10 to find the absolute uncertainty in capital T. So it is the range divided by 20. So let's check the first one. So this will be plus or minus 16 minus 15.2 divided by 20. That is 0.04. The next one, 18.3 minus 17.5 divided by 20. So that is 0.04 plus or minus. Then we have 19.3 minus 20.1 divided by 20. So still this is plus or minus 0.04. Next is 21 minus 21.8. I'm just subtracting. I don't mind about the negative. Divided by 20. So it is also plus or minus 0.04. The next one is 23.5 minus 22.7 divided by 20. It is still plus or minus 0.04. It appears as if it is the same. Then 24.1 minus 24.9 divided by 20. So this is plus or minus 0.04. So those are the absolute uncertainties there. Then for log, to find the absolute uncertainty in log, we can find the log. You can absolute uncertainty in log of t, for example, in seconds. You can find the log of t minus the log of t minimum, the minimum value of t. Or you can find, this is the same as the log of t maximum minus the log of t. Or you can find the log of t maximum minus the log of t minimum, then divide this by 2. So I'll just take one. I normally take this one here. So for the first one, remember the number of, when I find the log, the number of significant figures becomes the number of, it becomes the number of decimal places. So that is a rule. The number of significant figures become the number of decimal places when I take the log. When I take the log. For instance, if I find the log of 1.56, there are 3 significant figures. It means log of 1.56 will be 3 decimal places. So let me first find the log. Log of 1.56 is, I'll take 3 decimal places because there were 3 significant figures. So this would be 0.193. The rule allows you to write more but not less than 3. So this will be plus or minus. Let me first find the logs first. Then log of 1.79, that is 0.253 plus or minus. Then I have log of 1.97, 0.294 plus or minus. Then I have log of 2.14, 0.330, 0.330. You should be able to round off correctly. Then log of 2.13, sorry, 2.31. That is 0.364. 0.364, round off correctly. Then log of 2.45, that is 0.389 plus or minus. Okay, now let's find the uncertainties in each of these because I've showed you how to find the uncertainties. So I'll just use maximum, log of the maximum value of t minus log of t. So let's check. The first one, I'll find log of the maximum value of 1.56 is 1.5 plus. So that is 1.56 plus 0.04. That is the maximum value of t. Then minus the log of just the t, which is going to be log of 1.56 only. So this is 0.01. So this is 0.01. 0.01. I may write, for uncertainties, I can write them to one significant figure. Okay, let me check the second one. Or you can write 0.011 to have the same number of decimal places. To be 0.011, that is also fine. A mixture is fine, but plotting is the challenge. Then I'll have log of 1.79 plus 0.04, that is the maximum, minus log of 1.79 alone, which is going to be, I think that is 9 point, that is 0.0.00, is it 0.001? Let me see, 1, 2, 3. No, it is 0.01. So round off to the nearest number of significant figures. So that is 0.01. I'll just write 0.01 or 10 if you want. Then the third one, I have log of 1.97 plus 0.04, then minus log of 1.97. So this is, I think this is 0.09. So this is 0.09. Okay, then log of 2.14 plus 0.04 minus the log of 2.14 alone, which is 0.08. 0.08. I hope I'm writing these values correctly. No, this is 0.008. This should be 2 zeros. 1, 2, 3. That is 0.08. I have to check this again. Log of 1.97, log of 1.97 plus 0.04 minus log of 1.97. So that is 0.009. This is 0.9. I have to check this one again. Log of 1.79 plus 0.04 minus log of 1.79. So this one becomes, because 9.5, that becomes, I think this is, this will be 0.010 if I round off, because the 9 will be rounded off. Okay, then let's continue. Log of 2.31 plus 0.04 minus the log of 2.31. So that is 0.007. 0.007. Then the next one is log of 2.45 plus 0.04 minus the log of 2.45, which gives us 0.007. 0.007. So those are the logs, those are the uncertainties. They range from 0.011 up to 0.007. Okay. So having done that, plot a graph of log of t against log of m. Okay. So log of t against log of m. So we have to plot these points. Now let's start plotting. I think I'll write the points here for me to easily plot. I'll write the points here. 1.56. Now we are plotting log of t against log of m. Log of t against log of m. So the first point is, I'm not supposed to write here, but because I don't want to keep going back on the previous page every time. So I think the first one was 0.193 against 2.190, 0.253 against 2.312, 0.294 against 2.398, 0.330 against 2.484, 0.364 against 2.550, 0.389, is it 89? Yes, 0.389, and this is against 2.613. Okay, so I'm going to plot this. It is not easy to plot a graph on. It will be hard, especially when it comes to drawing a straight line, but I'm going to try my level best. So let's start. 0.193 on the this is y-axis, this is x-axis. So 0.193 against 2.190. So the scale here is 2.2 minus 2.1, which is 0.1 divided by 10. So the scale here is 0.01. On the x-axis, one box is 0.01. This is on the x. On the y, one box is 0.2 divided minus 0.18, that is 0.02 divided by 10. Am I correct? 0.2 minus 0.18. That is 0.02 divided by 10. That is 0.002, I think. Yes, 2 zeros. So one box is 0.002 on the y-axis. So I'm plotting 2.19. So this is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9 against 0.193. So 0.19, remember every box on the y-axis is 0.002. So this is 182, 184, or if you want to know how many boxes to add on 0.18, you just say okay. The point is 0.193 minus 0.18 divided by the scale, which is 0.002. So that means I'm going to add 6.5 boxes. So 1, 2, 3, 4, 5, 6.5. So this is the point. So if this is the point, I'll say I'll put a mark there and I'll circle this point. Now the circle is supposed to be very small. The circle is supposed to be very small, but because I'm plotting on a computer, it is very hard. I can expand this. Okay, so I think I can now redraw this. I can make this to look. So 1, 2, 3, 4, 5, 6.5. So it should be here. And I will draw a small circle around there. So that is approximately the point is in the center. Then the other point is I'm plotting on the x-axis 2.312, on the y-axis 0.253. Okay. So you must be patient with my computer. So I have to plot 2.310 So remember on the x-axis, one small box was representing 0.01. So I'm looking for 2.312. So I will simply say, okay, 2.312 is after 2.3, so I'll say 2.312 minus 2.3 divided by the scale, which is 0.01. I'm trying to find how many boxes I add on 2.3. So I'm adding approximately one box. So I'm adding approximately one box. Okay. Then on the y-axis, I'm plotting 0.253. So 0.253, 0.25, 0.253. So 25 is in between here. 0.253, 25 is in between here, so let me check. So I have 0.253 minus 0.24 because the next value there is 0.24. Then I divide this by the scale, which is 0.002, to find how many boxes I add there. So I'm going to add 6.5 boxes. So 2.312 against, I'll add 6 boxes, 1, 2, 3, 4, 5, 6.5. So it is around here. Remember the other one was 2.312 and it was 1 box 0.2, so it's around here. Remember you should make the circle clear so that it's not considered to be a ball, a blob. 1, 2, 3, 4, 5, 6.5. Okay, so I think that is the point. Then the next one is, now I have to fit this onto the graph because it is giving me a lot of headache. So the next one is 0.294 against 2.3, 0.294 on the y-axis and 2.398 on the x-axis. So 2.398, I'll say 2.398 minus, it is between 2.3 and 2.4, so I'll say minus 2.3 divided by the scale, which is 0.01. So I'll add 9.8, approximately 10, so it's almost 2.4 on the x-axis. It's almost 2.4 on the x-axis. Then on the y-axis, I have to plot 2.398. 2.398 minus 2. What am I doing? I've changed this. 2. Sorry. I'm plotting on the x-axis 2.398. So I say 2.398 minus 2.3 divided by 0.01. That was 9.8 small squares added to 2.3, which is approximately 2.4. Then on the x-axis it is 0.294 minus 0.294 minus, it is above 0.28, so I'll say minus 0.28 divided by the scale 0.002. So I'll add 7 squares. So this line is 2.4. So on 0.28, I'll add 7 squares. 1, 2, 3, 4, 5, 6, 7. So the point is approximately here. Okay, so that one is also done. Then we have 0.33 on the y-axis. 0.33, so I'll plot 0.33. 0.33 minus, it is just above 0.32, so minus 0.32 divided by the scale on the y, which is 0.02. So I'll add 5 small squares on 0.32. So I add 5 small squares. 1, 2, 3, 4, 5. Okay. But then on the x-axis, I have 2.48, 2.48, and 2.484 minus 2.484 minus, it is very close to 2.4, so I'll say minus 2.4 divided by the scale, which is 0.01. So I'll add 8, almost 8.5 small squares on 2.4. So 8.5 small squares on 2.4. So 1, 2, 3, 4, 5, 6, 7, 8.5, almost 8.5. So it is approximately here. So I'll mark this point with a circle. That is the point I'm plotting. Remember, this circle should be as small as one small square, but because I'm plotting on a computer, that's why it is hard for me. Okay, then the other point is going to be on the y-axis. I have 0.364. So that means I will add, you can check how many squares you add on 0.36. 0.364 minus 0.36 divided by the scale 0.002. You add only 2 squares. Then on the x-axis, it is 2.550. 2.550. I think 2.55 is in the center. 2.55 minus 2.5 divided by 0.01. It is exactly in the center. So I'll count 5 on the x-axis, and then I will count 2 on the y-axis. Now what is this? So 1, 2, 3, 4, 5 on the x-axis, then 1, 2 on the y-axis. So this is the point. So I'll circle that point. It is exact at that cross, not in between. 1, 2. So it's exactly here at the cross. Okay. Then the other one is, so this is done. The other one is 0.389 on the y-axis against 2.613. 2.613. So let me see, 2.613 minus 2.6 divided by the scale 0.01. I will add almost 1 small square on 2.6. Then on the y-axis, I have 0.389 minus 0.38 divided by the scale, which is 0.002. So that is 4.5. So 1, 2, 3, 4.5 in the center. But the other one was 1 and 1.3 squares, so it is approximately here. Okay, so that is the graph. So I have to reduce this to be able to draw the line of best fit. So I will have to reduce this. You will bear with me. I will have to reduce this to be able to draw the line of best fit. So I'm trying to balance the points to draw the line of best fit. I don't know if it will be visible, but I'm trying my level best. Okay. So I try to balance the points. I may not draw the best line of best fit because I'm drawing on a computer. but yours can be better than mine, no problem. So I'll draw the line. Yeah, I think this is better. That is enough. You can draw a better line than this. You try to balance the points so that if not all points are on a straight line, at least there's a point above and a point below the line. So that will be the line of best fit. So you label this. You have to label this line of best fit. So I will label this line of best fit or best fit line. That is best fit. Okay. Then I have to plot the error bars. I have to plot the error bars, which error bars are required. Include error bars of log of t. So we are going to plot 0.007, 0.007, 0.008. Because log of t is on the vertical, the error bars are going to be vertical like this one here. So I'll just write down the error bars here. So we have to plot 0.011, 0.010, 0.009, 0.008, 0.007, 0.007. I think that is all. 1, 2, 3, 4, 5, 6. I think those are 6. Yes. Okay, let's now plot. For the first one, it was 0.011. Okay, so remember the error bars are on the vertical, so I have to choose to use the scale when I'm plotting these error bars. So I have to divide 0.011 by the scale, which is 0.002, to know how many squares are those. 0.011 divided by 0.002. So those are 5.5 small squares. That is 5 squares above and 5 squares below. So remember this point was in the middle of the box, so that is a half. 1, 2, 3, 4, 5. So this will be stopping here. Then a half upwards. 1, 2, 3, 4, 5. So it will stop here. So I'll just do these horizontal lines with my vertical line. So when you use a ruler to draw these bars, they look so nice. My students always do very nice things. So you just pass the pencil twice, and this error bar looks so nice. Okay, I'll even increase the thickness for these error bars so that they look better. Okay, then the second error bar was 0.01. So 0.01, let me check with my calculator. 0.01 divided by 0.002. Those are strictly 5 small squares. So 5 above and 5 below. Remember this point was in the middle of the box. So a half, 1, 2, 3, 4. Then it stops in the middle of the box because it's 5 above, but remember the point was in the middle. So the other half means the point should be at the center here. Then a half, 1, 2, 3, 4. Then in the middle here it is another half to make it complete. So I will join this point with my ruler. That is the error bar. Then the next error bar was 0.009. So 0.009. So I'll check with my calculator. 0.009 divided by the scale 0.002. So those are 4.5 small squares. So because this point was just on the line, I'll count 4.5. Downwards, I have 1, 2, 3, 4.5, which is there. Upwards, I have 1, 2, 3, 4.5, which is somewhere there. So this point was very close to the vertical line. So 1, 2, 3, 4.5. So it is in between here. So I'll draw the vertical bar here. Please draw your lines better than mine, because mine, I'm drawing them on a computer, so that is the problem. That is the biggest problem. But this line should be passing through the center of the plotted point. Maybe let me try to erase it and redraw it. It should be passing through the center of the plotted point. Okay, then the next one, did I skip a point? No, this is supposed to be the third point. So I have to pull 4.5. 1, 2, 3, 4.5. It is in the center of the box. 1, 2, 3, 4.5. It is in the center of the box. Okay. So this is going to be the point here. The other one is 0.008. I think those are 4 boxes up, 4 boxes below. So 1, 2, 3, 4. So there are 4 boxes above. 1, 2, 3, 4, 4 boxes below. So the error bar will be something like that. Then the next one is 0.007. I think those are 3.5 boxes. So we have 1, 2, 3.5 below, and 1, 2, 3.5 above. Please use a ruler for these horizontal lines, which I'm drawing with my free hand. It's because I'm drawing on a computer. And I draw the vertical error bar. That would be the bar. Then the last one is also 3 above and 3.5 above and 3.5 below. We can check if you're not sure. 0.007 divided by the scale, which is 0.002. So those are 3.5. So remember, this point was in the middle of the box, so it is a half already. 1, 2, 3. So the horizontal line will be there. Then a half upwards. 1, 2, 3. The horizontal line will be there. Then I draw the vertical line. Okay, so I'm now done with my error bars. If you are using a pencil, which is very neat and well sharpened, the error bars look very nice. Then next, we are going to draw the line of worst fit. We have two choices. You can choose the steepest or the shallowest. So I have to reduce this again, because I want the graph to fit on the same page to be able to make a judgment. So there are two ways. You can join, you can even use a different color for that line in an exam, because it is a very simple line which you make a judgment once. You could even use a pen for that line. So I'll use a different color. Let me use green for that line. In an exam, you can use a different color. The line of best fit should cross through all the vertical error bars you have drawn. If not, you must adjust the method. The first simplest method is to put a ruler to the top error bar and to the bottom error bar and check and see if all the error bars would be crossed by that line. For instance, if I try this, putting to the top error bar up to the bottom of the bottom error bar, and I try to draw my line like that. If I try to draw my line, I see that all the error bars have been crossed by that line. If I join the top of the top error bar with the bottom of the bottom error bar, I see that all the error bars are crossed. So this is going to be a correct line of worst fit. So I will just label this line worst fit. So I will label this worst fit. Then the next thing I think is to find a gradient. Next thing is to find a gradient. So since it is to find a gradient, I must draw a triangle. You also have two options. You can choose a triangle. You can choose two triangles, one for each line, or you can do the same triangle for both lines. But putting in mind that the triangle should cross through points which you can easily read. So I will try to magnify this. And the triangle should cover up the largest part of the line, the largest part of this line. So I'm looking for the points which I could take for my triangle, so that is good enough. Okay, I could take this point and this point. I'll use a different color for my triangle. So let me use yellow. Okay, so I'm taking these 2 points. I'm drawing the same triangle for both lines, so there is no offense. Okay, I choose a point where the lines cross the error, but I don't choose in between boxes. So now I have also to choose at the bottom the best points for these triangles if it is possible. If it is not possible, I can choose independent points for each line. Okay, there are these 2 points here. So I am drawing my triangle to go through those 2 points. So I can prolong it downwards. Okay, so that is the triangle for both lines. So I'm going to use it to find a gradient. So for best, I'll just write out the points um, down here. Of course, you're not supposed to do this, but because I don't have one to go back to every point. So for the best fit, for the first point on the x-axis, best fit is in blue. So I'm reading this point here, 2.21222324. So we have 2.24. Then for the worst fit, the x coordinate is 2526. So this is 2.26. That is 26. These are the x coordinates. Then for that is initially. Then the second x coordinate, they have the same second x coordinate because of this vertical line here. So the second x coordinate is going to be 2.6 for both. No, it is 2. This is 2.9, 2.59, 2.59, 2.59 for both. Then for the y coordinates, the y coordinate is the same for both. This is 0. Because this is 0.202, 204, 20, so 2.02, 202, 204, 206. Okay, I'll just subtract 0.22 minus one box, which is 0.002. So that is 0.281, and the y coordinate there is the same for both. So this is 0.218, 0.218. Then I'll check the second y coordinates. For the blue, it is one small box on 0.38, so it is 0.382. So this is 0.382. Then for the worst fit, which is the green one, it is how many boxes? 1, 2, 3 boxes. That is 0.386. 0.386. I've written these values here because me, I am doing on a computer. For you have a question paper where you can always just transfer values to the point for the gradient. So Okay, so I had to record those values down so that I don't always move backwards. So next is to find a gradient. So because I need to include the absolute uncertainty, so I have to find a gradient for the best fit and a gradient for the worst fit. So gradient for best fit, I'll say gradient best fit. This is going to be, I'm going to use the best fit values. So the change in the y values we had is 0.382 minus 0.218 divided by the change in the x values 2.59 minus 2.24. That is the gradient for the best fit. Then the gradient for the worst fit, I'm using the values I've been writing in the graph. Our gradient for the worst fit, the y values we had 0.386 minus 0.218 divided by the x values we had 2.59 minus 2.26. Okay, so this is going to give me the gradient of the worst fit. So let me check the calculator. 0.382 minus 0.218 divided by 2.59 minus 2.24. So this is giving 0.469. 0.469. Then the next one we have 0.386 minus 0.386 minus 0.218 divided by 2.59 minus 2.26. So this is 0.509. Because it's 09 repeated, so it is 0.509. Then the uncertainty. The uncertainty is going to be the difference, 0.509 minus 0.469. So 0.509 minus 0.469, which is 0.04, 0.04. So I'll write here the answer as 0.469 plus or minus 0.04. The number of decimal places here doesn't matter as long as there's not one decimal, not one significant figure. Or you could write 0.47 plus or minus 0.04. You write the best value and difference in the two values, which is the uncertainty. Okay, sorry I had to use more time because I was drawing on the computer, so that is not my fault. As long as you understand the graph, there is no problem. Then determine the y-intercept of the line of best fit. So we use y equals to mx plus c. So it means c is going to be equal to y minus mx. So I'm going to use one of the values for the best fit, which I wrote here, the x value and its corresponding y value, 2.24, 0.218. So c for the best fit is the y value is 0.218 minus the gradient, which was 0.469 times x. The x value is 2.24. So times 2.24. So 0.218 minus the gradient 0.469 times 2.24. So this is automatically negative. So this is negative 0.833. So the y-intercept is negative 0.833 if I round off. They say do not include the absolute uncertainty, so it is not necessary. Okay, then, but if they had wanted us to include the absolute uncertainty, then we would get C for the worst fit using the worst fit values, and then the uncertainty in C will be the difference between the two. either C for the best fit minus C for the worst fit. So we just find a difference. You get C for the worst fit using the worst fit values and the worst fit gradient. Then you subtract. Remember, the uncertainty is always plus or minus, so there is no problem. Then using your answers to A, C Roman 3 and C Roman 4. Roman 3 is the gradient, Roman 4 is the y-intercept. Determine values of K and Q. You need not to be concerned with the units. Do not include the absolute uncertainty. So remember from where we started from, initially in the first page, we saw that the gradient was Q and the y-intercept was log 2 pi over root of K. Gradient is Q, y-intercept is log 2 pi over K. So I'll just use those ones here. So the gradient is equal to Q. So we don't need to mind about the units. So this is 0.469. And we say the y-intercept was equal to the log of 2 pi divided by root of K. So the y-intercept, remember, is negative 0.833. So I get the ant log. The ant log would mean that 2 pi over root of K is equal to 10 power minus 0.833. That is the ant log. So it means if I try to find K, then cross multiply, K will be equal to the square root of, no, not the square root, because K was the square root, it is the square. K is going to be equal to the square of 2 pi divided by 10 power minus 0.833. This is squared. I made K the subject here. Cross multiply, divide both sides, then remove the square. Remove the square root by squaring. So I'll now press the calculator. Shift ant log of minus 0.833. Then I have 2 pi divided by that answer. 2 pi divided by the answer, then squared. So it is going to be 1829.6. 1829.6. Okay, that is K. 1829.6. Then use your answers. Use your answers to D. Using your answers to D, determine the mass M needed to give a period of 1 second. So T is 1 second. So remember from the previous, the equation on the first page of T, they said T is equal to 2 pi M power Q root of over root of K. So I'm going to make M the subject. So T is equal to 2 pi M power Q divided by root of K. So I'm making M the subject. T root of K divided by 2 pi is equal to M power Q. So it means M is going to be the Qth root. So the root of Q. T root of K divided by 2 pi. So I'm now going to substitute M is going to be equal to the root. So here this will be the root of course root is a power, so I'll just write a power. I'll put power 1 over. So this will be into brackets. T is 1 second times the root of K, which is 1829.6 divided by 2 pi, but this will be power 1 over Q, because if you are finding square root of a number A, it is the same as A power a half. Now I'm finding root of this is not the Qth root. I don't know whether it exists, Qth root. So it is power 1 over Q, which is power 1 over 0.469. Okay, so 1 second, so it is 1 times root of 1829.6 divide by 2 pi, divide by 2 pi, then power, wait, which one is, or the root? No, I'm not good at using this calculator to find the nth root. Nth root. Okay, I have to use shift then. So shift nth root. So this will be root of 0.469. And in the brackets, I have the answer. So this is going to be 59.7. You can press the calculator correctly. 59.7, 59.72. So this is 59.72 in grams. Okay, so I think that is going to be the final value for M without mining about the units, because in the previous part we didn't mine about the units. Here it's only the period in seconds. So I think the answer is going to be 59.72. Okay, I think I've tried my level best, although it took a lot of time. It's because of the graph. Plotting on a computer is not easy, but I've tried my level best. So until next time, I'll try to solve more papers, paper 5s, even though it's not easy. Stay blessed. Bye bye.